Hi, Alice.
Hello. Hello,
Hello,
Xian.
Xiang. So, yeah, I'm sorry I did not have time to go over the thing that you sent. Yeah, I had another call, which is also why I'm a bit late. So, yeah, can you please take us through? So this discontinuity with respect to what variable? Okay. So, okay, you're really interested in discontinuity in P or in M or in either? Because sometimes there is also below the outside, there is also a power, which could be M to a power or P to a power. I don't know what it is here. There is both of them. And there is also M minus P. So I think we have to decide which one we keep fixed and which one we want to take a discontinuity with respect to.
I think this, Ainan, I think this power is actually from after the discontinuity has been calculated, right, Xian?
Okay, right. So what is the original expression?
So it's just m squared to power epsilon.
Right. So do you keep m squared fixed and look at the discontinuity in P? Okay, good. So that's a P discontinuity. Fine. Okay. Yeah, carry on. Yeah, sorry. So remind me, last week we just deduced what the discontinuity of this hypergeometric function was. What have we done? Is this? I vaguely remember that we look at analytic expression. Right. Right. You verify that this is exactly correct. So may I suggest that, every time you finish a bit of a calculation, like establish this result, you write the whole thing in LaTeX, right? So all this derivation, we don't want to need to go back to these handwritten notes where there may be typos and things like that. I mean, keep it, but if you have notes that are tidy and are correct, that would be very useful later on. Okay, yeah, now I remember. So yeah, you have a discontinuity of a 2f1 ABC of z, and you have a formula that is written by some other factors multiplying by another 2f1 of 1 minus z. Okay, times 2 pi I. Okay, let's go back to what you wanted. Okay, how do we define this maximal cut? So this is the maximal cut at leading order in epsilon or the maximal cut? Where? Where? So
It's the basis function for the maximal cut space for the sample.
I understand. Yeah. So can you show me what it is? Yeah. Mhm. One must bubble. One must sunset. Oops. One of the maximal cuts. Okay. Mhm. Okay, very good. So okay, I understand. It is this maximal cut. Well, uh, let's see. I think the normalization of this maximal cut in the paper is a normalization that's, I think from your perspective, is a little bit arbitrary. It's because what was the motivation for the normalization that was chosen? Motivation was that when you compute the coaction, or we can put it differently, when you compute the period matrix, then all the diagonal terms look like 1 plus order epsilon, and all the off-diagonal terms are of order epsilon or higher. So that somehow fixes the normalization, because, right, if yeah, it fixes the normalization such that it would be exactly 1 plus order epsilon. Yeah, so, but from your perspective, this is, I don't think you can regard that as, fundamentally the right choice. It is some choice. It is just some choice, I think. Oh, okay. No, I don't quite understand this ratio that I mean, this 8 pi I epsilon times m over p to the epsilon. What is it? Okay. What have you divided? You look at the equation 20 or 19 there in the paper. You divided what by this expression? Yeah, well, I think my question is not clear. What have you divided? What is the numerator? What object have you divided by the maximal cut?
Maybe I can help explain what Xiang is trying to say. So,
Yes.
so what Xiang has divided, he has performed the discontinuity operator on the uncut integral, and then
Okay.
he found some answer. He
Okay.
did some analytic continuation on that answer, and then after finishing with analytic continuation, he divided by the basis of one of the max cuts, one of the basis max cuts factors.
So sorry. Now I'm lost. So first of all, you took it before the analytic continuation. After you computed the discontinuity first time around, you divided that by the cut, and you got 8 pi I. Yeah, you got this one, and then you took the result. You made some analytic continuation relations, and then took the discontinuity again. No, no, or what?
Let me also try to explain, just add some extra explanation to that. So both are after applying some analytic continuation. So both are doing some analytic continuation. The one was done using one particular analytic continuation, and the other one Xiang did a combination of three analytic continuation.
Okay, yeah, okay. I think I start to get the picture more or less. So when you take a discontinuity, you take a discontinuity in a particular region. So what was the region in which you took it? The initial one. When you took the discontinuity, you referred, remember last time we discussed this, that I think I referred to the region where p squared was larger than m squared, and both were positive. So did you use this region when you computed the discontinuity? Okay. Now, each of the analytic continuation results is valid in different under different assumptions, right? So when you say that you can relate 2f1 of z to 2f1 of 1 minus z, this is valid for example, for z smaller than 1 and positive, because if you take z which is negative, for example, then 1 minus z is going to be larger than 1, and you'll be running on the branch cut. So you know, one of the functions that enter is not well defined, at least for real z. So this analytic continuation is a way to define it on this sheet or on the other sheet, but you don't get the same answer on both. So basically what I'm saying is that each of the analytic continuation results has some natural region of validity where all the functions are well defined, and in some cases it would take you to a region where some of the functions are not well defined. So let's look which ones you used. Okay, good. No, it's correct interpretation. If you use the relation precisely outside of the region of validity of that relation, then yeah, then you get something which is not well defined. I mean, it would, yeah, it would probably be correct up to some 2 pi I, but you're interested in the 2 pi I's.
What is a bit strange is that the answer differs by a kinematic ratio to a power of epsilon.
I agree.
This shouldn't be region independent. The region dependent. This should be completely region independent.
I agree. I agree. It looks a bit funny.
Oh, excuse me for a moment. Sorry, there's something.
Okay. No, I agree. So one thing I can ask is the following, or I can suggest each of the functions that you computed, you can check them numerically in the relevant region. So it's very, very useful to use numerical evaluations to verify what you're doing. So if you have a relation, you put numbers in both the left and right hand side, and the numbers should match the region that you think about Z as admitting, and you see whether this is correct. Okay? And when you have this ABC, it's also useful to think about epsilon as being negative, because epsilon is regularizing some infrared divergences. So it's really correct in the region that epsilon is negative, or should be correct. So I suggest that each of the, whenever you use an expression, you check it numerically before, and you'd see that if you're going outside the region, it would not work numerically. And it may be that the relation is just wrong because it's typed wrong, but then you'd immediately discover it by putting the numbers in. So one of two things: either the relation itself is generally wrong, or the relation simply doesn't hold in the region. Now, both of these things you can immediately identify if you do these numerical checks. Yeah. So at the moment, it's hard to know what exactly happened, because the ratio M over P, as Aris is saying, does not look like something that is true up to 2 pi I. It's just not correct at all. So it more looks like one of the relations that was used missed some factor or something like that. But that, again, you can easily identify by doing some numerical checks. Okay, so let's move on and just leave this exercise, I mean, for you to finish later on. Okay. So I think, yeah, you already have quite a few things just from this discussion to check the relations, to summarize what we have done before about analytic continuation, and to finish understanding the relation between the maximal cut and the discontinuity. Okay. In P, the channel cut and the discontinuity in P. Okay. By the way, this 8 is a bit funny. I think, okay, we might be able to understand the factor of 4 related to normalization that we have implemented in order to diagonalize the system.
But it's 8 pi I, which means probably
it's 2 pi I times 4. I would expect it to be 2 pi I, but it may be that we normalize things by a 4 in addition, and then it becomes, instead of 2 pi I, 4 pi I, 4 times 2 pi I.
In the paper, you show the sum equation after 420 in the paper, discontinuity with respect to p squared. Can you show this again? Because remember, there was a factor of -4 epsilon.
No.
Yeah. If you,
Okay. Is this the, yeah, that might be precisely the thing. Yes.
So it seems the same to me up to a minus sign, but the minus sign could be because it was a different order of discontinuity. It was like one minus the other versus.
Yeah, exactly. The discontinuity can be defined in two different ways, whether you take the upper minus the lower minus the upper. So just try to figure out which one it is here. Hopefully it's consistent between 421 first equation and 421 second equation. But in one of the cases, it's discontinuity with regards to M and the other with regards to P.
I think by M, you mean in this case, M going from positive to negative, from my understanding.
What do you mean positive to negative? It's always between something minus I epsilon, something plus I epsilon.
Yeah, so M squared.
M squared M squared minus I epsilon versus M squared plus I epsilon. So the real part is not playing a role. I mean, it's always in the same real part.
Yeah.
Okay, so I think, so you know how to do that. So both discontinuity relations you can find, right? 421, both discontinuity relations you can find. Now let's try to think more generally how we want to proceed. So I think we said that this example probably cannot teach us so much. And we want to have a situation where we have more channels, more propagators that we can cut that belong to different channels. So I suggested to look to begin with the bubble triangle. No, for the did I suggest that? Party hat or yeah, bubble triangle, or how do you call it? Double-edged triangle.
Oh, party. There's three names for
ice cone. How is it? Cream? No, ice cream cone.
Yeah, ice cream cone. Callum calls it ice cream cone. Yes.
Who called it that?
Callum called it that.
Callum.
Yes.
I see. Ice cream cone.
Yes. Yes.
Okay.
Yes.
So, I mean, we can call it many things, but this diagram, yes. So we decide to look at the lower diagram, that is Appell F4. And what do we want to do with it? Okay. So which integral representation have you used? I mean, I saw that, yeah, I show you the sophisticated one, which is called Kumar's representation. And I don't remember what gamma 1 is. Yeah. Yeah, so remind me what gamma 1 is. So you have to look at 85. It's Moto and Kita, I think. Ah, no, it's Goto Matsumoto. You have the paper? So I cannot see it very well. Let me enlarge here. Okay. So yeah. So can you put it? Is it on the Dropbox already, or? Please put it there, and then I can more easily have a look. Oh, yes, yes. Very good. Okay, thank you. Yes, that's very good. Yes. Delta 1. So if we look at the deltas, if we look in figure 2, Yeah, I think that figures 1 and 2 define the domains of integration. So you have in 2.6, you have delta I, and these delta i's are described in figure 2. So which one of them are we interested? Well, okay. So that's a prior question. So first of all, that's remember why I asked what you do with m. So in the previous case, we had p squared and m squared, right? So the hypergeometric functions depended in that particular case on the ratio p squared over m squared, and externally you had m squared. So if you wanted to take a discontinuity with regards to p squared, it affected only the argument of the hypergeometric and did not affect the prefactor. Now, if you now consider a case of this triangle that has a certain combination of scales on which it depends, let's call them P1, P2, and P3, right? Squared. So we're I know. At the moment, there is not so much I can write. This Appell F4 depends on what? On the result. Let's look. I think we called it Xi and eta maybe at some point, which is P1 squared over P3 squared, and eta is P2 squared over P3 squared. Okay. So now let us say, for example, that we are interested in the discontinuity in P2, okay? That means that we better choose P1 squared and P3 squared to be fixed and not touch them, and only modify P2 in such a way that we discover some discontinuity. Now, if we look at the integral representation of the Appell F4, in fact, we can look at the series even. From the series, it is clear that this series is going to be a series in xi to power n and eta to power k, right? And this series with some coefficients that depend on n and k. Now, as soon as this eta would go beyond 1, this series would start to diverge. Okay? And that somehow should be reflected in the integral representation, because if the series diverges, then it means that there is a branch point in the corresponding integral representation, right? So we are interested to look at the integral representation in the region where, so for example, if the discontinuity comes from the Appell F4 itself, then it should come from the situation where we go above and below the axis eta, the real axis for eta, when eta is larger than 1, because there is a branch point starting at eta equals to 1 on the real axis, and any value larger than 1 on the real axis is not smooth to go below or above, from below to above through that real axis. Is it clear? Maybe I can share so that make sure that this point is clear. Just a second. Okay. Okay, no audio, content. So I'm just saying that if the series for the Appell F4 that depends on A, B, C, and C prime of eta, of psi and eta, it looks something like sum of n and k from 0 to infinity times some coefficients c, n, comma, k. This series here diverges if eta is larger or equal to 1. So if we have an integral representation, we would expect a branch point at eta equals to 1, independently of what psi is. And now this is the complex eta plane, and I don't care what psi is, it's just fixed, because I'm only playing with P2 when P1 and P3 are fixed. So then the axis, this is the real axis, and that's the imaginary axis. And then this black line represents the branch cut. So this point is eta equals to 1, the real part of eta equals to 1. And we should expect that if we go from here to here, below the axis, above the axis, we get a discontinuity. That's the expectations based on the physics, essentially. Based on the, I mean, I don't know, it's not yet physics, but based on the properties of this function. Even seen as a series, it must have such discontinuities. So now let's try to think about the physics here. So I'm asking what happens when I take a discontinuity on P2. Imagine that P2 is formed by two particles like that. Let me say the following. I mean, you can imagine that P1 collides with P3. Both of them are incoming. And you are interested in producing these two particles. So let's say that this is W plus and W minus. And this is a top loop. No, then it's not so good. So because then that would be a bottom. So that would start having masses here. No, okay, I didn't want them to be massive. I want this to be massless. So let's just not have too much of a physical situation here. So these are massive. So let's say P1 squared is time-like and P3 squared is time-like. And then if also P2 squared is time-like, if let's see, if also P2 squared is time-like, I know that P2 is P1 plus P3 in the kinematics that I mentioned. And for any P2, I would say like this, for any P2 for which this process goes through, this would be a discontinuity. There would be such a discontinuity because imagine that, there is an amplitude here that is not zero. Now, if you cut through this line, you're basically asking the question, is it possible that these particles here, this one and that one, would be on shell? And the answer is yes, it is possible that they would be on shell because there is some center of mass energy here, and with appropriate momenta, these can be on shell, just taking the okay, this is this one. Just taking the momentum of these two. So they can be on shell, and it doesn't violate any momentum conservation or on shell conditions. So kinematically, this is allowed that this would be a final state, right? So I would expect that if these are time-like momenta, there would be a discontinuity because this diagram would have an imaginary part. Okay, that's a general physical expectation. If this internal loop is extremely heavy, then it's not going to have a discontinuity. Why? Because you cannot kinematically produce, if this is extremely heavy guy, then you'd not be able to produce it on shell, and therefore there would not be such a final state. So then there would not be a discontinuity if this one is very heavy. But we assume that this blue one is zero mass. So there should be an imaginary part. Okay, so now all we want to do is to understand what is this imaginary part. And for that, we look at the integral representation. So let us look at this integral representation that we have in this Motokita. And I think we have several integral representations here. Because the statement is that 2.6, for example, if I integrate over the delta, if I choose, you see, I get equation no number. The equation in lemma 2.1 on the next page. So I get an Appell F4. So each of so these are different representations of Appell F4 in terms of some integral. Maybe we can regard the defining one as F1. F1 is defined with delta 1. And if I'm not sure what delta 1 is. I think it's the most complicated one, unfortunately. What is that? Delta 1. let me just go up a little bit to make sure that I don't want to say something wrong. What is delta 1? Okay, yeah, it is the most complicated one. Yes. So delta 1 is explained. I never managed to fully follow that, I remember. So if you look at on page 64, you see delta 1 is written as delta plus some various funny looking circles. Okay. So the delta in figure 1 is this the inside of the triangle that is drawn between I1, I2, and I3. You see in figure 1 on the left. And then these kind of funny looking circles, these are these cylinders that encircle the boundaries of this region that is between the two, encircles these boundaries. So it's a fairly complicated region of integration. We can read what it says about this region. Delta 1 is the formal sum of the two-dimensional real surface delta, which is this triangle that we see, with boundary components I1, given in figure 1, where this oriented circle is a positively oriented circle in the T1 Ti space, starting from the projection of II to this space and surrounding the divisors Ti equals to 0 and Q, where delta 3 is a positively oriented circle with a small radius in the orthogonal component of the divisor L. Okay, now let's look at the figure 1. Are you looking at figure 1? Okay, so I think that the divisor L is this line that is this diagonal line. I can show you the definition. If we go up, what is L? Just want to find the definition of L. Somewhere it should appear, this L. I don't find the L, but I will be able to find it soon. It's a bit annoying. Yes.
Is it not in the paper? Is it not?
It's definitely in the paper. So page 68. Page 68, you see the definition of L and Q. Let's just memorize them because, so what you see is that L is 1 minus T1 minus T2. So that's a diagonal in the T1, T2 plane. And Q is T1 times T2 minus T1x2 minus T2x1. So this one looks like a hyperbola thing, right? Because it in the T1, T2 real plane, it looks something like fixed value of Q corresponds to T2 being 1 over, or some fixed value over T1. You see? If T1, T2 equals fixed, you ignore the linear term. If you ignore the linear terms, for example, for x1, x2 equals to 0, then Q equals just the product of them. So fixed Q corresponds to T2 equals that fixed number Q over T1. And that means that this looks like a hyperbola like that. The L looks like a diagonal that cuts a triangle out of the plane T1, T2. Now let us look back at figure 1, and now we recognize what we see. In figure 1, the line that looks like this hyperbola is this line that you see. I mean, maybe I should share this one. It would be easier. I share this one. So you see this line here. No. This line here, is it clear where my cursor is? That is Q. And this line here, that is L. And now we can read this again. Okay, we don't need to read because I can just tell you what it said. So what it said is like that. We are trying to describe an integration contour in the complex plane of T1, T2. Okay? We have integrations like that. T1 and T2 should be thought of as complexified. Okay? In the simple case, it goes in the plane, but really sometimes we need to go outside of the real plane to understand it. So this triangle that is here between I1, I2, and I3 is really in the real plane. But more generally, we should think about this axis T1 as having an orthogonal direction, which is the imaginary part of T1. And similarly, for T2, we should also think about this kind of a plane where there is a perpendicular one, which is the imaginary part of T2. Okay? So we should really think about T1 and T2 as 2 different planes, but we cannot draw 4 dimensions. So we draw just the real section of that. So now, now that we have in mind that T1 is really a plane, complex plane, and T2 is a complex plane, now we can understand what I1 and I2, what this kind of oriented circle is, I1 and oriented circle I2. So the oriented circle I1 is a cylinder that surrounds both the Q1 line and the T1 equals to 0 line. So this cylinder wraps both lines. And this I2 cylinder wraps this horizontal axis and this Q type hyperbola. And I3 is only this oriented circle here wraps the diagonal 1 minus T1 minus T2. So at least in principle, we understand what the integration region is. But we cannot write it as an integration region in the real T1, T2 plane. So now I don't know whether it is possible to work directly with this I1 because of this complicated boundaries. But that's the representation that they use as the defining one. Um, now let's try to think about the branch points. I think to understand the branch points, we might not need to think too much about these cylinders. Why? Because all we need to understand is whether the factor 1 minus x1 over t1 minus x2 over t2 develops a negative sign. I think that as soon as this factor here becomes negative, then we have a branch point. Now, x1 and x2 are the kinematic variables that of the Appell F4 in this definition, right? This x is representing x1 and x2. So this is the components of this is psi and eta. X1 and x2 is what we define psi and eta. So it's x2 that becomes larger than 1. So if x2 becomes larger than 1, and the t1 and t2 are restricted to be within the region that we discussed, is this factor going to go negative, to become negative? Now, let's see. So you see, this is the question that has to be asked to understand whether there is a branch point based on this integral representation. Yeah. Let me write it differently, and I think it would be maybe clearer. So I don't know. This is just a second. Let me find. Maybe they write it already. Yeah. Okay. Okay. You see this. Let's look at this. Well, maybe it's hard to see it immediately, but this is exactly the integrand that we had before. Okay. So Q, remember now, let's try to think about the region that we just discussed. The region that we just discussed in this plane was confined. It's internal to this delta 5 area. It's basically between these curves here. So if Q is positive, you are on one side of it. You see, if you have Q raised to a power, Q vanishes on this line. On one side of this line, let's say above, is positive, and below, outside this line, Q is negative. So that means that the point where Q equals to 0 is the boundary of this integration region 5. And I think it's almost the boundary of 1, except for this loop that they make here. So something interesting happens on the boundary of 5, or boundary of this boundary when Q is 0. Clearly, there would be a branch point there. Now, we can try to understand what the branch point is in terms of the variables that we care about physically. So let's look at Q. Q is T1, T2 minus T2 x1 minus T1 x2. We know that this one is positive in the integration region. Okay, so basically the statement is that so long as delta 5 is within the region 0, 1, 0, 1, we are not going to have a branch point. Okay. No. No. Let's see. Um, okay, let me try to think about the analogy with the 2f1. The analogy with the 2f1, we have 1 minus x, 1 minus uz to some power. I need to share with you this screen again. Okay, so in the 2f1 integrand, we had du u to a power, 1 minus u to a power, and 1 minus uz to another power. When do we get a branch point? We get a branch point if, and only if, z is larger than 1, because the integration region of u is between 0 and 1. So for any z in absolute value smaller than 1, in fact, for any z, let's take z real. For any z smaller than 1, the factor 1 minus uz is positive for all the points within the integration region. Okay? So now let's take the analogy for this quantity. So we are looking for what are the conditions on x1 and x2 such that, let's for simplicity assume, okay, what is the simplest example here? I'm looking now at the paper to get. Okay, I don't see a representation in terms of 5. I tend to choose this one. Let me just see that we have a representation in terms of 5. Mm-hmm. Mm-hmm. Maybe we should use another one to as an example. So let's try to use, for example, F2. If we use F2, okay. If we use F2, then the integration is over delta 2. Okay, delta 2 is defined between the regions like that. That Q of T1, T2, X1, and X2 is negative. L is negative, I think. Remember, L is 1 minus T1 minus T2, so L is negative.
Why is L negative? Because it's above the line. It's above the L line.
I thought the L is 1 minus T1 minus T2.
Correct.
So if I go for large T1, then L is negative.
True. Yeah.
So I think L is negative and Q is negative because we just said that above this line Q, let's check that, right? Q was what was Q? I think it is this combination here. It's T1, T2 minus T1, X2 minus T2, X1. So I can divide, so I can write T1, T2 times 1 minus X2 over T2 minus X1 over T1, right? So this quantity, when is it positive? So let's assume that X1 and X2 are positive. And then when we go to large T1 and T2, then we get positive Q. Okay. So it's true that above, so if this is my Q, this part Q is positive, and this part here Q is negative. Okay. So in the region delta 2, T2 is above a certain value, is larger than some T2 star, which is the point where Q is L. T1 is positive, and also T1 is smaller than T1 star, which is the point where Q equals L. And the rest of the condition, the most important conditions, are that both Q and L are negative. Okay. So the algebraic equation that we have to solve is what are the conditions on x1 and x2 such that within this entire region that I denoted here, all of the factors have the same sign, and I think this is, let's see, the only tricky thing is Q, right? Because if I start modifying the x's here, what are the conditions on x1 and x2 such that
well, really, you need to determine T1 star and T2 star, right, to do this. Because if you do, you will be able to write the contour for T1 and T2.
Yes, I should be able to write the contour and in principle integrate over it, but I'm trying to still formulate the question in a clean way. So here, so let's remind ourselves what happened in the 2f1. With one of the factors in the integrand was 1 minus uz to a power. And we identified a situation like that. If z is larger than 1, then this integration region brings us from a situation where this factor is positive to the situation where this factor is negative. Right? So if it's larger than 1, then within this region we have a branch point. We have a situation where one of the factors is 0 within that integration region. So now, can it be that within this integration region, if we fix x1 and x2 somehow, can it be that within this integration region, for some T1 and T2, this would be positive, and for other T1 and T2, this would be negative? Now, I have a problem, but because the definition here is that Q is always negative. Okay, it's always negative. Okay, I start to understand. I think that I mean the picture that we see here. What is it? I mean, the picture that we see in this figure is only true for certain x1 and x2.
It's like the 2f1, right? The 2f1 is true for small x.
Exactly. The picture is only true. I mean, this is really the integration region, how it would look if x1 and x2 are both smaller than 1. So what I suggest to do is to draw figure 2. How would figure 2 look like in case that x1 and x2 vary? And I think what we will see is that if x1 or x2 become larger than 1, then this would not be the correct picture anymore. Let's try to see what would happen in the 2f1 case. In the 2f1 case, we have u. We integrate u between 0 and 1. And because we take z smaller than 1, then this factor, so we integrate in this region. Now this factor has its 0 here at u equals 1 over z. Now, yeah, my problem is that here, in this definition of delta 2, yeah, I use Q as my boundary. So that is not going to work. So I think we need, in order to do that, we need to look at the definition that does not use Q as a boundary. Problem is that Q is always part of the boundary. So yeah. Yeah, I don't know how to solve this. So in this set of definitions, Q is always part of the boundary. Let me try to see.
Will that stop being the case when you find T1 star and T2 star? Because if you find T1 star, T2 star, you really have an integration region for T1 and T2 with respect to the x's are in the integration region, I see.
Yeah. Okay.
Yeah.
So I'm just using these regions, I cannot make the analogy complete because the definition of the integration region depends on Q. So this is equivalent. I don't know whether you can see my iPad still. Yes, you see. Yeah. So look. Let me tell you a little bit about these bounded regions so that you'll see what I'm talking about. Let's use this 2f1 as a definition, as a example. You see that there are 3 branch points here. Actually, there are 4. 3 you see immediately. One is when this vanishes, that's 0. One is that this vanishes, that's here. And one is this vanishes, that's here. Where is the 4th one? it's a bit hard to see, but that's at infinity. If u equals infinity or minus infinity, then, you know, if you change variables u to 1 over u, you'd see that that's another branch point. So that's the fourth one. So now, the homology group is, think about it as a vector space of all the possible independent integration regions that you can form between these boundaries. So if you if you write this 2f1, you can integrate. So if you, okay, this is a definition with this blue region here, right? Now, someone else can choose the branch points, say, between this and that. And someone else can choose between this one and that one. You know, and yet another one can choose between this one and the one at infinity. So there are 4 now. But actually, if you try to play with these, you'd see that by changing variables and analytically continuing, these 4 are actually dependent on just 2. So the blue, for example, and the orange are enough to span the space. You don't need, it's just a 2-dimensional vector space. So if you define one of them, let's call it gamma 1 as the integral from 0 to 1, and gamma 2 as the integral between 0 and 1 over z, that's gamma 2 and that's gamma 1, then you can express also the others. For example, the integration between the green one or this pink one, you can express them in terms of these 2, gamma 1 and gamma 2. Now, what they have done here in this case of Appell F4 that we are looking at, the homology group is 4-dimensional. Now, they claim that the basis, this 4-dimensional space, well, I lost a little bit the picture, but that the 4-dimensional space can be drawn from this delta 2, the crazy delta 1 that we saw in the beginning, this one, which I think is delta 3, and what was delta 4?
It's delta 5. Delta 1 is a subspace of delta 5, right? It's a sub-contour, I guess.
It cannot be a sub. Yeah, okay. Yeah, maybe. Let's see. It's, delta 1 is this one plus the boundaries.
Yes. Okay.
The boundaries are like that. Yes. And delta 5, which is this entire region here. Okay. Anyway, 4 independent contours are the basis of the homology group of the F4. We don't need more than 4, because if we were to choose some complementary region, or maybe even this region that goes here, that would be expressible in terms of the remaining ones. Okay, that's the statement. Now, let me try to explain the problem that I encountered before. So, the contour gamma 2 that I defined here in the 2f1 case is the contour that ends at the point u equals 1 over z. With this contour, this object here is always going to have the same sign. You see? Because by definition, this contour ends at the point where it changes sign. So with this contour, we are not going to be able to identify the discontinuity, because it's defined putting the endpoint on this boundary. On the other hand, if we take the 0 to 1 integration, this one, and now we play with Z, and we compare the case where Z is outside to the case that Z is inside, then we see a difference. Because when Z is outside, then this is real. The whole time the integrand is real. When Z is out, that's when Z is outside. If Z is inside, then suddenly part of this region, it is complex. Okay? So for gamma 1, we can identify the two situations. While for gamma 2, we cannot, because it is always the boundary. That's the defining feature of gamma 2. And that was exactly my problem with these contours here. These contours, they are using Q as the defining endpoint, like Z was. And therefore, I cannot use them to go in and out of the region. That's the issue here. Now, I could choose this as my integration region. That triangle, for example. If I choose this triangle as my integration region, now, based on this homology theorem, I should be able to express the result of this dashed region in terms of the integrals that are given with the deltas. Okay? I should be able to do that. However, I would notice that depending on the values of x1 and x2, sometimes this curve would look like this, and sometimes this curve would look like this. You see? So sometimes it goes inside my dashed region, and sometimes it never touches the dashed region. And that's precisely analogous to what happens when this point Z is outside or inside. If it's outside, then I will not have a branch point, because I would never change the sign of my integrand in this entire triangle. And if it is inside, then I will change the sign while integrating over the same triangle. Okay? So at least we understand the principle. Now the question is how to use this, how to use this to, I see that there is another region D here. And I think D is also a useful one. Let's try to understand what the region D is. It's in the very beginning, there is this region D that is fine. Here. Here, yeah, equation 2.5 has the region D, G3.
It's defined on the first page, right? The very first page, 62.
D, I mean, this.
Oh, it's a different D, sorry.
No, it's, yeah.
It's a different
no, I mean the integration region D. the integration region D is defined in equation 2, is used in equation 2.5 to define an integral, okay? The question is, this integral, how is it expressed? I think the statement is that f4 of a, b, c, and x can be written as either 2.3, 2.4, 2.5. So if you use 2.5, you have to use G3 that's written below. So basically, that's another way of writing the integral over the region D. Okay.
Check page 65 for D, right? It's on page 65. In the middle of the page, it says D is the bounded connected component.
Right. That's true. That's true. Okay, so I think this can help us because here you see that x1 and x2 appear in different factors. Let's see. Or maybe not. Maybe not. And suppose I use the representation with D. And then I ask the question, for a given value of x, is my integrand, does the integrand have the same sign in all of D? Well, then I have to look at this expression, and my conclusion is that yes, it is defined precisely such that it has the same sign in all of D. So yeah, so this is not a good integration region in order to identify. You see, it has the same problem. It has the same problem in the sense that it is defined to be between the branch points of the two factors that appear here to power C1 minus A and C2 minus B minus 1. So if it is defined between these two branch points, then we can never explore the situation where you go outside of that region in order to get a discontinuity. Right. So I think that basically their definition are always in such a way that it's impossible to get a discontinuity. In some sense, it was designed this way. It's designed that the integrands would be real within the integration regions.
Well, may I say there's one thing, though, there's one condition that applies. This is because we're looking only at variables x1 and x2.
Right.
If we look at the 2f1 analogous case, think about the region from 0 to 1 over z.
Right.
You could do a change of variables. The variable of the 2f1 will stop being z, will become 1 over z. But now you can start examining what happens for the variable of 1 over z.
No, but it would still be, I mean, the branch point, I mean, there is no difference. The branch point would always be at the point z equals to 1, or 1 over z equals to 1. So that would not change. The issue is really that it's the following statement about the 2f1 again, that if we were to choose the region 0 to z as our integration region over U, then by definition, that integrand has always the same sign, because the boundary is defined to be the point u equals 1 over z.
You're right.
Okay. So now, I don't know. I did not explore all the options they have here. There are many regions that they propose. So obviously D depends on the other regions. I mean, one can. There are only 4 independent regions, basically. That's what I'm saying. And we can try to find a way to still compute the discontinuity using one of these integral representations. Let's see. Okay, what they say like that. Let's see. If C1 and C2 are not integers, then the Appell F4 with U contained in capital X. What is capital X? U contained in capital X. I don't know at the moment what capital X is spanned by the following 4. This is a cohomology basis, as far as I see. Aris, do you agree with me that this looks like a cohomology basis?
Yes. Yes. I have, when you already have one more point about the 2F1 analogous case with the change of variables. So I was looking at that.
Okay. Let me say the following. Xiang, let me give you an example of how it could work, right? Suppose you take 2.5 as your representation, and you do not integrate over D, but integrate over a region that's larger than D. For example, let's say that you integrate over the region which is bounded by one of the curves, 1 minus T2 plus T1, T2, X1, but is not bounded by the other region, but goes to a larger value, okay? Then at that point, a branch point would be generated precisely at the point where that factor vanishes. And that would correspond to the physical branch point we are looking for, because at that point, X2 let's see. What I want to say is that we would be able to blame X2 for the problem. For the fact that, so for some values of X2, it would be fine. And for some other values of F2, there would be a branch point. And that that's what I mean by blaming x2 for the trouble. So if x2 would be restricted in a certain way, it would be convergent. It would not be a branch point. And if x2 exceeds this value, then there would be. At the moment, we cannot do it because this is defined in such a way that it's within D, and D is precisely such that both factors are positive. So that's an example of how it could have worked if, with a different definition of a contour.
In principle, you can define any contour you want, right? But the key point is, what is the functional representation of this integrand over this contour that you will choose?
Precisely. And the statement is that for any contour that goes between any of the lines that we discussed here, it should be possible to write them in terms of some basis of integrals of f4 like that, right? It should be possible. Now, it's not always trivial, but it should be possible. And then, so all we need is to control this basis. Now, in this case, it's a little bit tricky to go between different representations.
Like I will add to this, in the triangle you showed earlier, this was essentially the representation where T1 and T2 are both integrated from 0 to 1, right? Oh no, that's
here I chose this is actually a reasonable region, I would say, because I choose T1 positive, T2 positive, yes, and 1 minus T1 minus T2 positive, exactly, which is precisely corresponding to L being negative. So these are factors that appear within your here. You see, it appears in equation 2.6. These factors all appear in equation 2.6. So this is definitely a valid region, this triangle. So in fact, I would say I would like to know what the integration, what is this in terms of Appell F4? I mean, I don't know what the answer is, but it should be expressible in terms of Appell F4 because it belongs to this homology class, right?
And I think this is not even that hard to do because you can find this region. This region is independent of X. You can do a change of variables and then.
So how can you relate that region to one of the other regions that are known in terms of F4?
Well, you could do it for the 0 to 1 region. For T goes from 0 to 1, T1 goes from 0 to 1, T2 goes from 0 to 1. And you could do a change of variables that maps the contours like that, and then you could see what the integrand looks like.
I think they do here an example of taking D to delta 2. That's a bit similar to what you just said. I mean, they're making a change of variables such that something that was originally defined in D becomes delta 2 in the new variables. You see this? At the bottom of page 67. So this is a change of variables from the S's to the T's, such that the T's are defined in terms of S's, let's say, and in this way, in the first set, it is D, and in the second set, it's delta 2. So that's a miracle, right? It took one and turned into another. So we are basically asking a similar question, starting with a triangle that I mentioned, this big one, and can we find a change of variables such that we write it in terms of the other regions? And then since the other regions, we know exactly what they are in terms of Appell F4, then we found a triangle in terms of Appell F4. And for the triangle, it's fairly easy to understand when Q intersects it and when not. Because when Q intersects it, that would generate a branch point, which is not there otherwise, right? So that's an example of how we could solve this problem.
I want to show something about what I said before with the 2F1. Can I share something fast? Because
yeah, please go ahead.
I think you need to stop sharing it for a moment. So for me.
Yeah, at the moment, let's see. I have to do it here on the iPad.
Yes. So let me share this Mathematica. Oh no, where is it? Oh, I'm sorry. I'm sorry. Yes, here. Okay. So maybe we can forget about this. So just look at this, okay? So this is a 2F1, okay?
Mm-hmm.
Now, if this 2F1, so the integration variable is x, the argument is u. If this 2F1 is integrated from 0 to 1 over u, okay?
Yes.
Then this change of variable takes it from 0 to 1.
Exactly. Yes, that's equivalent to what they have done in that ST transformation for the 2F1. Yes.
So indeed, that's correct. So what happens is, so if you do this change of variables, what do you see? Indeed, you see that this thing over here, it doesn't have a branch cut. This is the thing raised to the power c from above. So this thing, of course, now it's from 0 to 1, it doesn't have a branch cut. But what has a branch cut is this thing for u greater, for u smaller than 1. Where does this come from? This comes from the fact that 1 minus x had the branch cut before for u greater than,
no,
for u smaller than 1.
It had a branch cut, but because x did not run between, because x was not running between up to 1.
Yes, so x was surpassing 1. Exactly.
Yeah. If u is larger than 1, no, smaller than 1. Yes, if u is smaller than 1, then it would be surpassing 1.
So how is this analogous to the previous case? So maybe this polynomial q is indeed smaller than 0, greater than 0 for some region. But that doesn't mean that t, for example, is necessarily
always positive.
Yeah, always positive. So maybe the branch would lie on t.
Well, in the triangle it would be, but
yeah, in the triangle it would be, but for some other.
So I think, I mean, a good example is this L curve and the Q curve. So I mean, we can consider two situations. One is when the L curve cuts the Q curve twice, and one is that when maybe that the L curve doesn't cut it at all. I mean, these two situations, yeah, I think they can both happen for certain values of x1 and x2. I think so. But yeah, I have still a little bit of problem with that because that's completely symmetric in x1 and x2. We would like it to somehow be, I mean, maybe the regions is delta 2 and delta 3 that we have to think about. Let's see.
I'll stop sharing this because that's.
So, we can think about the following. We can think about so let me draw it again. So, do you see it now?
Yeah.
So suppose I draw this one. So this is my L curve, and that purple one I didn't succeed to do the Q curve, but I think no. Somehow I need to make it. Yes. So that's my Q curve, and that's my L curve, right? And now what I want to say is that let's stay in the T1 positive, T2 positive quadrant, right? That's T1 and that's T2. We can consider the region Q. Now, remember that Q I think Q is positive here. Maybe I should do it in this, and L is positive in this region, right? So we can consider the following regions. One is called triangle, and that's defined by L positive, ignoring Q. And the other one is defined by saying Q negative. That's another region. Okay, let's call this gamma 2 and that called gamma 1, right? Now, if I take the difference between gamma 2 minus gamma 1, that becomes delta 3 plus delta 1 minus delta 5. Do you agree with this relation? Okay. So we know that delta 2, so this is not delta 1, this is delta 2. We know that each of these can be expressed in terms of the Appell force that they give. That means that we at least have one combination, gamma 2 minus gamma 1, which is also expressed in terms of the Appell four combinations that they give. So it's enough for us to find either gamma 1 or gamma 2, and then we find the other, right? So we're trying to get more shapes here in this plane. And then I think it should be possible to identify the branch points. There is also this region D, which to me is curious. I think that D is also interesting. You can also look at Rx, which I don't know what it is. Okay, so yeah, I think we can define the task of finding a discontinuity of this Appell F4 on the triangle. I mean, this Appell F4 that you have in equation C34, is it? I forgot. Do you have the paper? I think it's equation C34, if I remember rightly. Okay, so I think, so let's try to find the discontinuity of that one for psi one for x1 or psi between 0 and 1, and for psi 2 between 1 and infinity, or well, not psi 2, or eta, or x2 between 1 and infinity. So that should have a discontinuity there, and yeah, I think we can try to define this as a task, because that would correspond to some physical region discontinuity of that integral, right? By the way, I think that the domain D, maybe the answer is given here in some way. Look at the beginning of this paper, the very beginning of this paper. They say that the series is convergent in the region that is bounded by this square root of x1 plus square root of x2 smaller than 1. So when I said that the series is divergent, I meant that if you want to make it divergent for x2 independently of x1, you make x2 larger than 1. If you want to make it divergent in x1 independently of x2, you make x1 larger than 1. They give you here a precise condition. They say that the series is convergent in this region. So that probably tells us that, yeah, the physical condition for which this would be divergent, convergent. And I think we can immediately understand what it means physically. So what we have is square root of p1 squared over p3 squared. Do you see what I'm doing? Yes. Plus square root of p2 squared over p3 squared smaller than 1. That's the condition for convergent series. Okay? Now let's assume that we are you see what this corresponds to. I think you see this immediately. So imagine that imagine that P3 equals just P1 plus P2, and these are just energies, and we are working in the center of mass frame of P3. So imagine that it's like you have a massive particle P3 that decays into P1 and P2, and these P1 and P2 do not have any more momentum. So they are sitting there. It decays and it's sitting there. That's precisely when this equality holds, because what happens here is that this is just P1 over P3, 0, plus P2 squared, P2, 0, over P3, 0, equals to 1. Namely, P1, 0 plus P2, 0 equals P3, 0. What is this? This is the threshold. This is the physical threshold. If you have a mass larger than the masses of 1 and 2, then you can decay to that. And of course, if you have more energy than P3, than the sum of the masses, of the rest masses, then you remain with some kinetic energy, but they can still be on shell. On the other hand, if you had a mass that's smaller than P, than the sum of the rest masses, then you simply cannot produce them. And then there would not be an imaginary part in this triangle, right? Because the triangle corresponds to, it can also be seen as P3 decaying into P1 and P2. And this channel would not have any discontinuity. Now it's this channel that we're talking about. So I think we can immediately understand the connection between the convergence of the series and the generation of an imaginary part. Physically, we know that there should be an imaginary part if this is violated. It should be real if this holds, and there should be an imaginary part if it's violated. Physically, we know that. Mathematically, we see that this is indeed what happens, because this is a property of this function. So we now see that, Appell F4 should indeed be physically the right description of that. It has the right analytic properties to represent the cut structure of that thing. As soon as we go beyond that region, there is an imaginary part, while if we are within this region, there should not be an imaginary part. And that's exactly what happens. So actually what I'm asking you now is to go outside this region and compute the discontinuity, because I want the imaginary part. So I'm telling you, okay, go outside this region by making P2 large enough, okay? And it turns out it doesn't even have to be larger than P3. It just has to be larger than what this tells you. So assume they're all positive. Then it just has to be such that this would be larger than 1 minus the square root of P1 squared over P3 squared, P3 squared. As soon as we get this larger, then there would be an imaginary part. So you can go to the region where it's still smaller than 1, this ratio, but it would generate some imaginary part nevertheless. So we don't really have to go to the region where it's larger than 1. Okay. So yeah, so I think this is also a very important point, because we immediately see that the mathematical properties of this function are consistent with the reality properties of the we expect from physics. Okay, I think this is enough for this point. So I suggest you read this paper a little bit more deeply and try to find a way to compute the discontinuity. And it might not be easy. I don't see immediately how to do it, but you should be able to at least be able to express this triangle and other regions here in terms of the Appell F4 using the regions that they have given. Yeah. What might be difficult is to use the region which is called delta 1, because that has this kind of complex boundaries. But the other regions are definitely easy to use. They are real.
So essentially, the idea is start with the integral expression of the triangle. The boundaries are clear. It's the area bounded by this triangle.
Yeah, it's what we call gamma gamma 1, where L is positive, and T1 and T2 are also positive.
So really, what is that? It's just, T1 goes from 0 to 1 minus T2, and T2 goes from 0 to 1.
Exactly. And if we can integrate, we don't actually need to integrate. All we need is to make changes of variables such that that would fall into an Appell F4, which we recognize. Of course, it will not be one Appell F4. It can be a linear combination of a couple of Appell F4s, right?
The thing about this, it doesn't, I think it's okay if you map it to going from 0 to 1. So if you use the traditional representation of Appell F4, right? Because no, that's not good actually. You would lose X.
Because then it's a bit complicated because you have to split the X.
Yes, exactly. Yes.
Yeah, I mean, I know that's a difficult one.
Yeah, that's another task. So basically, you have to restrict yourself from using the deltas here to see if you can do such a map, essentially. Now, for the deltas, to make it very explicit, Inan essentially has shown for what the boundaries of integrations are. There's some T stars instead of explicit boundaries, but these T stars is essentially solving some system of equations. So you will be able to write boundaries, I believe, in terms of x's essentially. And then you can write clear boundaries, and then by change of variables, you can see if you can match them. You can match the integrand of one with the other, or the boundaries. You can match the function. We don't know if that's going to happen, by the way. So we need to examine all cases and see if it happens. If it doesn't, it's actually something important, because this is very general. It's not a case by case thing. It's working with fours in general.
Well, I'm basically confident that the triangle and this other region that we defined with gamma 2 can be expressed in terms of Appell F4s. Yeah. And that I can be confident because these are within the homology family, going between branch points of the integral representations that they have. You just go between different branch points, right? So if we look at the equation, look at the integrand as they wrote it in the page 68. You have 4 factors raised to a power: T1, T2, L, and Q, right? These are 4 factors raised to a power. You should be able to define integration region as anything that's bounded between any curves in this family. That would fall within the homology group. So anything that you can form out of this, and including this triangle and gamma 2, they should be expressible in terms of these integrals themselves. That's essentially what they prove, that this is the homology theory, right? That this is the basis of the homology group. Yeah.
So as a first thing, Xiyang, try to find all the boundaries of so you can write explicit integrals essentially. And if you have questions about it, we can discuss next week. We can discuss before the meeting with him.
Yeah, by the way, I see that they play a little bit with delta 5 as well, mapping it to other regions. There is another example of a change of variables later on page 73. So yeah, this is this figure. it doesn't look very easy. Mm-hmm. Okay, there are interesting relations here. Yeah, I think it's worthwhile reading more of it because they have done really difficult things. Maybe, of course, we don't need all of what they have done, but they basically have full control of the period matrix. All of the integrals that can be formed between these boundaries, they are understood. Yeah. Yeah, it's very different, and it's a very different integral representation. You see, I think it's because it has a different integrand, completely different integrand. I don't know how they are connected, but it's a very different integrand. So it's not easy to relate. It's both different integration region and different integrand. So I don't know how they are connected. That's a good question. Maybe they explain it, but I don't know. It's definitely not something that's trivial to see. If you have different integral representations of this function, it's extremely hard to relate them to each other. You need to work hard for that. But once you have an integral representation with different contours, for example, then it's simple geometry to relate. So, yeah. Let's see. Yeah, I think it's worthwhile reading it because I mean, as I said, they've done very complex. So look at lemma 4.4. There are new definitions of these Fs, and then they define a certain period matrix using these definitions. Right. Mm-hmm. Okay, let's finish now. I think we should all look at this paper a bit more and then discuss again. Okay, then thank you very much. Yeah, okay, no problem. Aris, do you want to continue our discussion from yesterday? Aris, you are muted, so...
Yes, we can do a little bit of that if you want, yes.
Okay, let me take a short break then. So, okay. Yeah. Bye, Xian. Yeah, bye-bye.